Good morning, everyone. So in this lecture, we will continue with the second part of thermodynamics, and it's going to be the last chapter in this course, in which we're going to talk about the heat engine, the entropy, and the second law of thermodynamics. So after the introduction, here are the topics that we are going to discuss in details. So the heat engine, we will introduce them, and we'll talk about the second law of thermodynamics. We will differentiate between the reversible and irreversible processes by defining them. We will show the importance of the Carnot engine, and finally, we'll talk about the entropy. So in the previous chapter, we introduced the first law of thermodynamics, and we saw together that this was simply a statement of conservation of energy. So in other words, the first law of thermodynamics states that a change in the internal energy of a thermodynamic system, it can occur as a result of energy transfer, whether by heat, by work, or by both of them. But this first law of thermodynamics makes no distinction between the heat and the work, although there is a difference between both. And also the first law of thermodynamics makes no distinction between the processes that occur spontaneously and those that do not. So for example, in nature, we only see that certain types of energy conversion and energy transfer processes that take place. And we don't see other processes that take place, for example, in the opposite direction, the same processes in the opposite direction. And there should be a reason, or at least there should be some law that explain why or what is the preferred direction for processes that occur in nature. So this is why we introduced the second law of thermodynamics. And the second law of thermodynamics, basically, it establishes which processes do and which do not occur spontaneously. So as few examples, let's actually see some processes that if they proceed in either direction, they would not violate the principle of conservation of energy, but they are only observed to proceed in one direction. Like, for example, heat flow from warmer body to cooler body, which is never seen to happen from the cooler to the warmer. إذا بتحطوا معلقة بقلب كباية الشاي والشاي سخن طبعا، فبتلاحظوا إنه المعلقة هي اللي رح تسخن والشاي رح يبرد. And heat flow, it never goes in the opposite direction. يعني بتلاقوا إنه المعلقة بردت أكتر والشاي سخن أكتر. For example, sliding a book across a table, it always converts mechanical energy into heat by friction, and we have seen that. We have seen that whenever you have an object on a surface, a given surface which is not smooth, then you have a friction, and you have always loss in the mechanical energy, which transforms into thermal energy because of the friction. Also, for example, if you have a rubber ball dropped to the ground, it bounces several times and eventually comes to rest. But actually, a lying ball on the ground, it never gathers internal energy from the ground and begins bouncing on its own. So there are a lot of observations. يعني إذا في عندكم طابة وكبيتوها مثل طابة التنس for example، تعمل كذا مرة كونتاكت مع الأرض وبعدين توقف على الأرض. بس إذا كانت طابة already موجودة على الأرض، ما بيصير في اكسشينج ما بينها وبين الارض، وبتاخذ internal energy منه، وبصير في عندها energy وبتصير ترجع هي بتمشي منها لحالها. So كل هول البروسيسز اللي هلا اعطينا عنهم examples هن عباره عن processes they occur only in one direction in nature, and they are never seen to occur in the opposite direction. So this is why we call them irreversible. And all processes that occur in nature, they occur in one direction and they are all irreversible. But we are going to discuss reversible and irreversible processes later on in slides بعدين. However, the point from this slide is to say that the second law of thermodynamics, it basically discusses the preferred direction for irreversible processes. And the most important implication of the second law of thermodynamics is the limited efficiency of machines. So here I want to go back to the point on the first slide when I said that the first law of thermodynamics does not distinguish between the heat and the work. And this is not correct. And one of the clear manifestation of this distinction هي إنه in reality ما فينا نعمل ماشين على قد ما بنعطيها heat بتطلع لنا work. So clearly there is something different between the heat and the work. So they cannot be treated both on the same in the same way. and هذا الشيء بنشوفه بالحياة الواقعية إنه بيترجم يعني عمليا بالحياة الواقعية in the limited efficiency of machines. مما يعني إنه إذا في عنا if you have a given machine that operates in a given cycle, and we have seen what is a cycle previously in the previous chapter, and if this machine it takes energy by heat and it expels energy by work, يعني بتاخد heat وبتعطيكم work بدل الهيت، ما ممكن تطلع نفس كمية قد ما عم تاخد هيت قد ما عم تعطي work. Always the amount of work given or produced by this machine is less than the amount of heat which is taken. So this is why we say that a machine that takes an energy by heat does not expel an equal amount of work, never expels an equal amount of work. And so this is why we talk about limited efficiency of machines. Yani a machine cannot be 100% efficient. So this is the manifestation, for example, of the distinction between the heat and the work, which is not discussed in the first law of thermodynamics, but it is discussed in the second law of thermodynamics. ومن هون رح نروح على الأول part بالchapter اللي تبعنا اللي هو about the heat engine. So what is a heat engine؟ اللي هي الهيت engine الماشين اللي حكينا عنها قبل شوي. So a heat engine actually is a device, it's very simply a device, as you can see in here, that takes in energy by heat. It operates in a given cyclic process. And what we mean by cyclic process, it's the kind of cycle that we have seen in the previous chapter, so which is composed basically of few processes like adiabatic, isothermal, isobaric, etc. And then after taking the heat and processing through and operating through a cyclic process, it expels back a fraction of that energy by means of work. So مثل ما نكون شايفين هون, this heat engine عموما, it consists of three parts basically. So it's composed of what we call a hot reservoir, which has a high temperature TH, hot temperature. You have the second reservoir, which is called cold reservoir, at TC to say T cold. And the engine is basically composed of what we call the working substance. So the working substance هي عمليا المادة اللي عم تكون هي عم تاخد الهيت وعم تعمل الورك. Like for example an ideal gas, this kind of things. So what happens is the following. How this heat engine it proceeds in the following way. أول شيء, the heat engine, it carries the working substance through a cyclic process. And again, what do we mean by that? We mean in this PV diagram, we had, this is the pressure as a function of the volume. And when we say cyclic process, we mean that the working substance, which is our subject in here, it will go through a cycle, which is composed of different pieces of processes, okay? So it could be, so only had a combination of different kind of processes, from A to B to C to D and then back to A. So this is the cyclic process we are talking about. And this working substance, when going through the cyclic process, it passes through different steps, which are three basically. So our step, the working substance, which is in here, actually it absorbs energy by heat from a high temperature reservoir, which we call the hot reservoir. So the first step, the working substance, it actually takes in heat from the hot reservoir. Then it goes through the cyclic process and then it expels work, which is given by here W engine. And then the energy is expelled by heat QC to a lower temperature reservoir. So at the end, there would be some heat which is still remaining in the system, and this heat is expelled back to another reservoir, which is called cold reservoir, because it's going to be at lower temperature. So this is from outside, what does it look like a heat engine, okay? Now, the point now is we are interested actually to determine the efficiency of this heat engine, because we have said previously that the second law of thermodynamics, one of its manifestation is the limited efficiency of the machine. So we want to show here how much is the efficiency of a given heat engine. For this reason, we will see what is the work done by this heat engine and how much energy is supplied to this heat engine. يعني عمليا لما نحكي عن الافشنسي احنا عمليا عم نحكي عن ratio ما بين what you give, what you gain divided by what you give. سو قد ايه عم تاخذ قد ايه عم تعطينا الماشين work على قد ايه عم تاخذ منا heat. This is how we see it. Okay, so let's do it. قد ايه عم تعطينا work؟ يعني هون بيطلع معنا هيدا W divided by Q. هي معناتها ال thermal efficiency. For this reason بهيدا السلايد رح نشوف شو هي ال W وشو هو ال Q. Okay, so first of all we know that the working substance goes through a cycle as we have seen previously. So it goes through this PV cycle, and at some point it goes from point A and it comes back to this point A, which means that delta U, the variation in the internal energy of this working substance, is simply zero, because it goes from one initial state and it gets back to the same state. So if delta U is equal to zero, then let's apply the first law of thermodynamics. According to the first law of thermodynamics, we know that that delta U is equal to Q minus W. And so if Q minus W is equal to zero, that means that the work done by the system, so by the working substance, is equal to Q. And of course, Q here is Q net. It's the amount of heat exchange with the surrounding. فإذا هي عبارة عن QH plus QC. Okay? So now we know what is the work which is provided by this heat engine. And so we can say very briefly that the net work provided or done by the heat engine is equal to the net energy transferred to it. يعني هي عم تاخذ QH بس عم ترجع QC. فبدنا نشوف شو هن هدول QH plus QC. أول شيء ال QH هي عبارة عن heat which is flowing into the system. So it flows into the working substance, and that means that QH is equal to plus QH. لأنه هيدي it's the heat added to the system. Now, about QC, QC is the amount of heat which is leaving the system. It's flowing out of the system. So إذا بدنا نجي نكتب QC رح نلاقي إنه QC هي عبارة عن negative value لأنه هي leaving the system. So this is why we write it as minus and then the absolute value of QC. يعني لحتى نقول إنه هون ال QC هي negative value. So بنحط minus وبنخلي ال absolute value ل QC يعني بنخلي قيمتها لحال. And so this is the heat flowing out of the system. So we end up with W, the work done by the working substance, is equal to QH minus QC as absolute values. And so now what we need to do is to define the thermal efficiency of this heat engine. So the thermal efficiency, which we call eta, or you can call it sometimes E, I mean, مع بعض المحلات. So the thermal efficiency of a heat engine is defined as the ratio of the net work done by the engine during one cycle to the energy input at the higher temperature during the cycle. So, in other words, بتشوفوا انتو it's the work, it's what you gain divided by what you give. What you gain is the work, but what you give was QH. انتو عطيتوها للworking substance QH, right? So we just replace W with its value. W هي عبارة عن QH minus QC divided by QH. So it's equal to QH over QH is 1, and then minus QC over QH. And so this is the expression for the thermal efficiency of a given heat engine. So this is a very general expression, and whatever is your heat engine, you can apply this definition for the heat engine. Now, let's just discuss, or let's make a few comments. So first of all, eta is equal to 1 only if QC is equal to 0. So in other words, you get 100% efficient machine if you don't have any energy that is expelled as heat to the cold reservoir. And this never happens in reality. So a heat engine with a perfect efficiency, which means with 100% efficiency, would have to expel all the input energy by work. يعني كل الهيت اللي عم تاخدها QH, it will have to expel it as W engine. And efficiencies of real engines are never 100%. They are all below 100%. And so here comes the second law of thermodynamics. So on the basis that the efficiencies of real engines are all the time below 100%, the second law of thermodynamics, as stated by Kelvin and Planck, it's given by the following statement. It's impossible to construct a heat engine that, operating in a given cycle, produces no effect other than the input of energy by heat from a reservoir and the performance of an equal amount of work. So in other words, this is what we mean by the second law of thermodynamics, that if you have this heat engine and you have a heat which is absorbed by the working substance QH from the hot reservoir, and then the heat engine would never produces an equal amount of work بكل بساطة. وبالتالي لازم حكما بالريل انجن يكون في عندنا بعد جزء هيدا الفيجر is impossible. So this engine is impossible. You would never see it. What's missing هو انه بعد في عندنا energy which is expelled to the cold reservoir and this is QC. هلا الفيجر صارت it corresponds to a real engine. مثل ما كانت قبل كانت it's impossible engine. And this is the second law of thermodynamics statement. انه عن جديد باختصار شديد the real engine always have an efficiency which is below 100%. So as you can see, the second law of thermodynamics is not a physical law as we see usually, like it's an equation. It's just a statement. It's not an equation. So let's continue with the reversible processes. So reversible processes and irreversible processes, what is the difference between the two? Actually, in a reversible process, the system undergoing the process can be returned to its initial state along the same path on a PV diagram. And every point along this path is an equilibrium state. So هذا الشيء بيعني التالي. And if you have a reversible process, then this can be drawn on a PV diagram, okay? A given curve along the PV diagram بغض النظر كيف هي أو شو شكلها الكيرف. And if you go from the initial states, if this system undergoes a process from the initial state I to a final state F, it can be returned, okay, from the final state to the initial state along the same path. يعني فيكم ترجعوا رجوع على نفس الكيرف. And every point in this path is an equilibrium state. And so this is why in PV diagram, all what you have are reversible processes. A process that does not satisfy this requirement is irreversible. So an irreversible process means that if you go from an initial state to the final state on a given path, you cannot go back from the final state to the initial state on the same path. And this is why you cannot draw it on a PV diagram, because on a PV diagram, every point along this path is an equilibrium state. And in irreversible processes, the system can go through in equilibrium points or states going from initial state to the final state. Okay. Now, although all real processes are all irreversible, كل البروسيسز اللي بنشوفهم بالواقع وبالحياة هي عبارة عن irreversible processes, but some are almost reversible. بما معناه إنه if a real process occurs very slowly, such that the system is always very nearly in equilibrium state, then the process can be approximated as being reversible. So إذا كنتوا عايزين تعملوا process اللي هو it occurs in nature in one direction, it doesn't occur in the other direction, فينا نحن نعمله approximation as a reversible process إذا كان عم بيصير بشكل كتير بطيء. For example, an isothermal compression of a gas very slowly by dropping grains of sands onto a frictionless piston. So if you have here, this is a given gas, okay? This is the piston, and then you drop few grains of sands كل شوي. بتنزلوا كم حبة رمل. انتوا عم بتنزلوا حبوب الرمل عمليا اللي عم بيصير انه عم تعملوا له compression، بس هو عم يروح من state, let's say PI in PI VI into another state PI plus DP VVI plus DV. It's an isothermal، بس بكل ما بين ال two states ما عم بيكون في تغيير للإكويليبريم، يعني عم بيكون all the time near an equilibrium state، وبالتالي كأنكم عم تمشوا على path from initial state to final state where every point is an equilibrium. فبهالطريقة بنقدر نعمل approximation لل processes which are real, which are irreversible to be reversible. Okay, so this is how we define reversible and irreversible processes. But once more about the reversible processes, these processes occur naturally only in one direction. You don't see them in the other direction. And as we have seen in the very first slide, we gave many examples, like if you have the heat flow always from the warmer body to a cooler body, هول كلهم بالحياة بنشوفهم in only in one direction. And those are non-equilibrium processes. So the system is not in thermodynamic equilibrium at any point until the end of the process. So only initial state and final state, they are equilibrium states. And all natural processes, they are known to be irreversible. So all the processes that we see in the universe, they are known to be irreversible. Okay. Let's continue with the Carnot. So the Carnot engine. So first of all, the Carnot engine is a heat engine, as we have seen previously. What does it mean, a heat engine? So it takes heat and provides or delivers some work. So it's a heat engine which operates in an ideal reversible cycle between two energy reservoirs. The importance of the Carnot cycle is that it's the most efficient energy engine possible. So if you have any other engine which operates between the same two energy reservoir, any other engine, it would never be more efficient than the Carnot engine. And this is the most important thing about the Carnot engine, which is actually an ideal cycle, and it established an upper limit on the efficiencies of all other engines. So it's like احنا بنعرف انه according to the second law of thermodynamics, that the efficiency of a real engine is always below 100%, and it never reaches the 100%. But it doesn't put any limit on this efficiency. فالكارنوت engine هو عباره عن الليمت يلي نحن ما بنقدر نتخطاها حتى يعني بما معناه نحن ما بنعرف انه ما فينا نوصل لل 100%، بس كمان نحن ما فينا نوصل لهيدي الكارنوت انجن، حتى نحن على طول بنكون تحتها ما دونها. It's the most efficient engine possible. And so this is why we say that the Carnot theorem, in the Carnot theorem, it states that there is no real heat engine operating between two energy reservoirs can be more efficient than a Carnot engine operating between the same two reservoirs. And so let's see, what is this Carnot engine and how does it proceed? So the Carnot engine actually it was introduced by a French engineer, and actually it takes place between two temperatures اللي هن TC و TH which ما شفنا قبل بالheat engine. It uses an ideal gas as a working substance, and it consists basically, so the Carnot cycle, is composed of two isothermal and two adiabatic. So you have here from A to B, it's an isothermal process. Then from B to C, it's an adiabatic, sorry. From C to A, it's isothermal, and then from D to A, again, it's adiabatic. So let's actually see what happens during a Carnot engine. So what happens is the following. The Carnot cycle consists of, as we have said, it's the first هون هي عبارة عن isothermal expansion، لأنه as you can see the gas, the working substance اللي هو ideal gas in our case, it goes from VA to VB, and VB is greater than VA. So we have an isothermal expansion during which the working substance absorbs heat اللي هي QH, which is the first part in this heat engine. And then it's followed by an adiabatic expansion, during which the temperature of the gas decreases from TH to TC. فإذا أول شيء بتاخد الهيت بأول part اللي هي الisothermal expansion at the temperature TH, of course، لأنه هون عم ناخد QH من الهوت reservoir. بعدين بصير في adiabatic expansion during which T drops from TH to TC. And then this is followed by, طبعا خلال هيدا البارت من ال B ل C, we have work which is provided, we have work which is delivered. Then from C to A, the working substance expels back the heat اللي هي QC. And then from D to A, it's an adiabatic compression بترجع للinitial state اللي لها، بيوقف السايكل وبيرجع ببلش من أول وجديد. So this is what happens during a Carnot cycle. Now, our point now is to determine what is the thermal efficiency of the Carnot engine. We want to see how much is this atom. So we can apply immediately the expression that we have already derived. And the thermal efficiency of a heat engine is given by 1 minus QC over QH. And now our goal is to determine how much is QH, how much is QC. Okay. So let's start. We have 4 processes that we have to discuss and study: AB, BC, CD, and DA. So let's start first with BC and DA. These processes are adiabatic. هون من البي للسي going from TH to TC and then back from TC to TH من الD للA. So those 2 processes are adiabatic, and we know that in adiabatic process there is no heat transfer, which means that QBC is equal to QDA is equal to 0. There is no heat transfer in these processes. So we have to look at AB and CD. So let's look at AB and CD. AB, just like CD, they are isothermal process. So it's an AB, it's an isothermal expansion. From C to D is an isothermal compression. بس بغض النظر, we know that during an isothermal process, delta U is equal to 0 for an ideal gas, لأنه delta U is equal to NCV delta T. والdelta T is equal to 0 لأنه T ما عم تتغير. So delta U is equal to 0, and therefore, according to the first law of thermodynamics, Q is equal to W. هلا قد ايه work done during an isothermal process? You remember in the chapter 20, I told you that we have to memorize this expression, so we can write down immediately that W is equal to nRT, ln V final minus V initial. And so we apply it in here, we end up with nR times TH, لأنه على ال AB احنا على temperature العالي TH, multiplied by ln V final over V initial, يعني VB over VA. So this is the work which is done during the process AB. And so we can, of course, deduce that QAB is equal to nRTH ln VB over VA. And in the same way, going from C to D, we can also apply the same expression which we have calculated in the previous chapter. So QCD is equal to the work done by the gas going from C to D. So it's equal to nR times TC, where here TC هي مش T للpoint C, هون هي ال T للcurve الموجودة عليها C, and by this we mean T cold, multiplied by ln V final over V initial, فبالتالي هي VD over VC. So now the point, we know what is QAB and we know what is QCD. هن عمليا WAB with WCD. But we need to determine QH and QC. احنا لازم نحدد أي هي من هالQ اللي هي QH وأي هي QC. How can we distinguish between the two? نحن بنعرف إنه ال QH هي البوزيتيف لأنه it's added to the system, وال QC هي النيجاتيف لأنه it's provided or expelled by the system. So let's actually let's examine these two. طيب بالنسبة لهيدي expression, so nRT, of course they are constant, so we don't look at them. We have to look at ln of this ratio. So this ratio VB over VA is greater than 1, right? VB over VA is greater than 1 لأنه ال VB أكبر من ال VA. مثل ما تكونوا شايفين هون احنا بحالة expansion وال VB is greater than VA. So this is VB and this is VA. And so here we can deduce that if VB over VA is greater than 1, then ln VB over VA is greater than 1 and WAB is greater than 1. And so which means that the QH هيبان انه هي البوزيتيف، فاذا ال QH هي equal لل WAB، فاذا هي equal لل NRT H ln VB over VA. نطلع على هالاكسبريشن ال VD over VC، ال VD is smaller than VC لانه هون كان في عندنا compression، فاذا ال VD over VC is smaller than 1، يعني ال VC اكبر من ال VD، عم ننتقل نحن على compression، فاذا ln VD over VC is negative، وبالتالي WCD is negative. شو معناتها WCD is negative؟ معناتها انه ال QC هي اللي equal لل WCD لانه هي negative، وبالتالي هي equal ل minus nRT cold ln VC over VD. So بمعنى آخر جينا كتبنا ال QC as minus and then the positive value. فهذا الشيء هون مختصر. فإذا we know that WAB is positive, which means that QH هي ال WAB لأنه ال QH positive. أما هون ال WCD بما إنه هو negative, so we are identified as QC. وبس على طول بنطلع الماينس لبرا لحتى نقول إنه هيدي ال QC هي النيجاتيف. الأفضل نكتبها بهالشكل، وبالتالي هون ال quantity اللي بتطلع معكم هي بتكون positive. So this is it. Now what we need to do is to divide QC by QH. So let's do it. QC over QH حطيت هون كل شيء بقيمته. So minus nRTC ln VC over VD divided by nRTH ln VB over VA. Of course, nr cancel out, and we end up with minus TC over TH times the ratio between ln VC over VD divided by ln VB over VA. But at this stage, we still have some work to do because VC, VD, VA, and VB, they are all unknown, as you can see here. على هال Carnot cycle, we only know two variables which are known. يلي هن TC with TH. Those are the only known variable. These VA, VB, VC, and VD, we introduced them, and so they are still unknown. So we have to find a way to express these volumes as a function of the temperature. بما انه نحن بحاجه لنلاقي ريليشن ما بين التمبريتشر وما بين الفوليوم، لانه نحن معنا فوليوم اللي هن ال VA, VB, VC, VD, and we need to express them in terms of TH و TC. اوكي، شو بعد في عنا شيء بالسايكل ما استخدمناه؟ بعد في عنا الكيرفز BC و DA. In these two parts of this cycle, the working substance undergoes an adiabatic process. ونحن بنعرف انه بالadiabatic process we have three relations, and one of these relations we have a relation between temperature and the volume, which is given by T times V to the power gamma minus 1 equal to a constant. So why not to use this expression to find VA, VB, VC, and VD as a function of the temperature? So let's do it. أول شيء خلينا نحكي بالبي سي. طيب بالadiabatic expansion again from the previous chapter we know that T times V to the power gamma minus 1 equals to a constant, which means that if this is applied between the initial and the final state, it's going to remain the same. فبالتالي we can write down TB VB gamma minus 1 equals to TC VC gamma minus 1. إذا بنحط كل شيء بقيمته، التي بي هي equal للتي اتش لأنه hot، واللي هون التي للبوينت سي هي equal للتي cold. اوكي، سو تي سي هون هي cold، وكل وحده بتضلها مضروبه بالفي بي والفي سي. بنفس الطريقه فينا نكتب الدي اي which is an adiabatic compression بس بهالحاله اللي بتفرق، بس again we can write exactly the same thing. So TA VA gamma minus 1 equals to DD VD gamma minus 1. So هون عم نشتغل على two ends point بهيدا البروسيس. And so we replace TA by T hot and TD by T cold. And now what we need مبدئيا هو احنا we need the ratio between these two. فإذا we can actually, or yeah, let's do it. So we can take out ال TH، خلينا نعمل ratio ما بين هول الاثنين. يعني we have to divide ال TH VB gamma minus 1 over TH VA gamma minus 1. That is equal to TC VC gamma minus 1 over TC VD gamma minus 1. هي هي. So من هالريشيو طبعا TH and TH cancel out، في TC and TC cancel out. بيطلع معنا انه VB over VA is equal to VC over VD very easily, which means that this ratio is equal to 1 لانه ln VC over VD هي نفسها VB over VA. So وكأننا عم نقول ln VC over VD divided by ln VC over VD, which is the same quantity, and that goes to 1. So if that goes to 1, then QC over QH is equal to minus TC over TH. بما انه نحن بالthermal efficiency عندنا 1 minus the absolute value of QC over QH, then we end up with 1 minus TC over TH. And so the efficiency of the Carnot cycle is only given by 1 minus TC over TH. So it only depends on the temperature of the two hot reservoir. It doesn't depend on anything else. And this is the powerness of the Carnot cycle. So again, eta only depends on the temperature of the two heat reservoirs. And as you can see, eta increases as TC is lowered and is increasing as TH is raised. So if you want to get the highest thermal efficiency for a Carnot cycle, you have to choose the hot and the cold reservoir, as the hot reservoir should have as much temperature high as possible, with low temperature reservoir to have as low as possible temperature. The efficiency is equal to 0 in case TH is equal to TC. يعني بمعنى آخر ما في عندكم difference ما بين the two hot and cold reservoirs. So of course in this case nothing is going to happen and the heat engine will not operate. Also, a few important things to say is that this equation اللي هي eta equals 1 minus TC over TH, نحن we have calculated, we have derived in such a way that we used the working substance as an ideal gas. But what you need to know is that this equation is valid, okay, whatever the working substance is. So all Carnot engines operating between the same two temperature have the same efficiency, eta equals 1 minus Tc over Th, irrespective of the nature of the working substance. So even if your working substance is not an ideal gas, you would still get the efficiency of the Carnot engine to be 1 minus Tc over Th. No real engine can be more efficient than a Carnot engine operating between the same two temperature. And as we said earlier, so this equation 1 minus Tc over Th, it sets up an upper limit to thermal efficiency of a real engine. يعني احنا بنعرف مثل ما قلنا حكينا قبل انه real engine it can never be 100% efficient. It's always below 100% efficiency. And what is this limit? What is this threshold? اللي ما بيقدر يتخطاه تحت ال100 هي ال efficiency of the Carnot engine. So this is it for the Carnot engine. Of course, you can apply the efficiency of a Carnot engine immediately. يعني انتوا بس مسؤولين انكم تعرفوا to memorize this expression eta equals minus Tc over Th for a Carnot engine. So if you're asked about the Carnot cycle efficiency, you can apply this relation directly. So in this part, last part, we're going to talk about the entropy. So the second law of thermodynamics, as we have seen, is not an equation as many familiar physics law. It's a statement of impossibility rather than equation, right? It tells us that there is no heat engine or machine that can provide an equal amount of work as the amount of heat absorbed by the working substance. And since it's not a quantitative statement, then maybe we can introduce a quantitative statement of the second law of thermodynamics, but we need for this a new state variable, which we call the entropy. What is the entropy? Actually, the entropy is a measure of the disorder of a given system. Isolated systems tend toward disorder. And to measure this disorder, we use the entropy. Now, in order to go more deep into this, this discussion, let's consider actually an infinitesimal reversible process, okay? It could be any infinitesimal reversible process, like an example, an isothermal expansion of an ideal gas, and during which heat is supplied to the system, and the system changes from one equilibrium state to another. So I will take in this case the example of an isothermal expansion of an ideal gas, but I'll make a comment at the end that even if you don't take this example, you will end up with the same result. So هدفنا من هذا السلايد انه نشوف شو ممكن تكون الاكسبريشن للانتروبي, okay? And this is what we are going to do. So we are talking about an isothermal expansion, right, of an ideal gas. So we know that the internal energy in this case does not change because du depends on temperature in the case of an ideal gas. And if there is no change in temperature, then there is no change in the internal energy as well. So applying the first law of thermodynamics, du equals to dq minus dw, we end up with dw is equal to dq. So the work done by the gas is equal to the energy added to the system by heat. But we don't know, so we don't know how much, we are looking for dq in this case, but we know how much is dw. So dw is equal to pdv, this is by definition. And since we are dealing with an ideal gas, then we know that P is equal, can be expressed as a function of the volume in the following way, هي nRT divided by V times TV. ما ننسى انه نحن هون عم نحكي عن isothermal expansion, so T is constant. And so from this expression actually we can get the following. dV over V is proportional to dQ over T, right? إذا ما نجي بس نكتبها بهالشكل هون من هالايكويشن شو بيطلع معكم؟ إذا بتقسموا dQ على nRT من تاني جهة بيطلع معكم هاي equal simply dV over V. So we can write down dV over V is proportional to dQ over T. يعني بمعنى آخر when you make an expansion والvolume تبعكم عم يكبر, okay? What does it mean? The molecules are now moving in a larger volume, right? عم يقدروا يكبروا بفوليوم أكبر يتحركوا لأنه صار في expansion. And so actually they have more randomness of position. صاروا قاعدين يتحركوا بفوليوم أوسع والبوزيشن تبعولهم بشكل راندوم قاعدين يتحركوا أكثر. فبالتالي the gas is a more disordered state. حيكون في more and more disorder as much as the expansion is يعني عم تكون اكبر. وبالتالي هل disorder اوكي هو له علاقه بقد ايه عم نعطيهم heat at a given temperature, where T here is a constant, of course. And so this is why from here it comes the definition of the entropy is that if dq is the amount of heat transferred to the system during the reversible process, then the change in entropy ds is equal to this amount of energy divided by the absolute temperature of the system. So from here it comes the definition of the entropy to be equal to dq over t. لانه الدي كيو اوفر تي هي اللي لها علاقه بالهيت، يعني هيدي الاكسبريشن يلي عم تعطينا عقد ما هالهيت عم بفوت عقد ما عم يعمل ديزوردر. وليش نقيناها بهالشكل؟ لانه طلع انه دي في اوفر في هي اللي بروبورشنال للدي كيو اوفر تي، والدي في اوفر في هي اللي بتعطينا بتخلينا نلمس قد ايه عم بيكون في ديزوردر، لانه عقد ما عم بيكون الفوليوم اكبر عقد ما عم بيكون في راندومنس اكثر وقد ما عم بيكون في ديزوردر اكثر. So from this slide, we know then now that by definition, the change in entropy when a system undergoes an infinitesimal reversible process, it is equal to the amount of energy added to the system by heat divided by the absolute value of the system. So ds is equal to dq over t. Okay, and this equation it defines the change in the entropy rather than the entropy. So the entropy is a state variable. Hell equation it defines how much we have a change in the entropy. Okay. So just one comment is that here, even if we don't take an isothermal expansion process نحن عم نحكي عنه, still we can always consider T to be constant. لأنه إذا عم تعملوا an infinitesimal process, infinitesimal mean يعني عم بيصير بوقت كتير قصير. فبالتالي the temperature of the system it will remain constant during very short time اللي عم بيصير فيه the process. So even though it's not an isothermal expansion of an ideal gas, still if you have any infinitesimal reversible process, still you will get ds equal to dq over t where t is a constant. Now هون شفنا فإذا الentropy definition of the change in the entropy for an infinitesimal process. Now what if we have an finite process, يعني عم بيكون في عنا process between very well defined initial state and the final state, and in general t will not be constant, right? So for a finite process where t is generally not constant, if dq is the heat transferred to the system following any arbitrary reversible process between two initial and the final state, then the change in the entropy between these two states is defined by delta S, which is equal to the integral of the S going from the initial state to the final state. And this is nothing else than the integral, so from I to F of dq over t. And now it depends on each, what is the process that you are talking about. حسب كل process بيطلع معكم dq شيء، بيطلع معكم t هو عبارة عن شيء ثاني، بتحطوا كل شيء بالاكسبريشن اللي له وبعدين بتقدروا تطلعوا الدلتا S. And as you can see from the expression that delta S, it depends only on the properties of the initial and the final equilibrium states. يعني عمليا delta S مثل ما شفنا قبل هي عبارة عن state variable. And if it's a state variable, then it's defined in a given state. فبالتالي delta S has the same values or the same value between a given initial and a given final state. Okay, بغض النظر عن الباثs اللي عم تقطعوا لتروحوا من الانيشال على الفاينل state. So this is why delta S it only depends on these properties of the initial and the final state. And also here actually the entropy change for an irreversible process. نحن هون كل شيء عم نحكي بالنسبة ل reversible process. يعني a process that is well defined and can be drawn on a PV diagram. If we are talking about an irreversible process, then we can consider the system to be between the same initial and the same final states, okay? And then we calculate delta S between this initial and this final state for any path between these two, any reversible path between these two, and delta S would be the same. لأنه عن جديد الانتروبي هي عبارة عن state variable. يعني إذا بتجيبوا delta S for a given system between initial and final state, فيكم تاخذوا any reversible process ما بين الانيشال والفاينل ستيت تجيبوا له الدلتا اس وبعدين ترجعوا تقولوا اذا كان irreversible process between the same initial and the final state فاذا دلتا اس هي هالقد وهالقد بنكون already اشتغلناها. Just one example of how to calculate, for example, the change in entropy. Let's suppose that you have an ideal gas which is undergoing a reversible process from some initial state to some final state. And you want to calculate the change in the entropy of the gas for this process. So how we are going to do? So we know that delta S is equal to the integral from initial to final state of dq over t, right? So we have to determine how much is dq. طيب لنروح على the first law of thermodynamics. The first law of thermodynamics, it states that du is equal to dq minus dw. But dw by definition is equal to pdv, so it is equal to dq minus pdv. بس نحن هون we need dq. So let's write down, then this gives back dq equals to du plus pdv. But the dq in the case of an ideal gas, it's nothing else than ncv dt. So this is why we end up with dq equals ncv dt plus we replace p كمان with its value بيطلع معنا nRt over v times dv. طيب اللي باقي نعمله انه نقسم الدي كيو على t ونحطها هون بقيمتها. فاذا شو بتقسموا الدي كيو على t you will end up with هون بيطلع معكم ncv dt over t plus nRt dv over t. فهون التي مع التي they cancel out بروحوا، يبقى عندكم ncv dt over t plus nr dv over v. And this is it. Now all what you need to do هون انه to make the integral. بالنسبه لاول انتجرال حيطلع معكم هي عباره عن n times c phi. هول الاثنين هو عباره عن constant so بيطلعوا لبرا. So integral of dt over t from of course t initial to t final. حسب الفاريبل الموجوده بالانتجرال ساعتها بنحدد شو هن الفاريبلز بالانيشال والفاينل ستيت بلس كمان ال nr هن عباره عن constant بيطلعوا لبرا integral ل dv over v. فاذا هون الفاريبل of interest هي dv فبالتالي لازم نحط from v initial to v final. الانتجرال لل dx over x هي ln x. سو هون بيطلع معكم هي عباره عن ncv ln t final over t initial plus nr ln v final over v initial. And so this is delta S. This is the change in entropy of the ideal gas for a reversible process, an arbitrary reversible process. شو ما كان البروسيس بيطلع معكم هي النتيجة. So this expression actually demonstrates mathematical proof that the entropy change only depends on the initial and the final state and is independent of the part between the states, of what happens between the states. يعني مثل ما نكون شايفين هون بالدلتا اس كان بس it figures out you have t initial t final, you have v initial and v final. ما في عندكم اي شيء بخص الباث نفسه ما بين الانيشال ستيت وما بين الفاينل ستيت. So now just one comment also about the entropy change in reversible cycles. So كل شيء كنا عم نحكي قبل هو كان عبارة عن entropy change in reversible processes. Now in reversible cycles, given a system that goes through a reversible arbitrary reversible cycle، ما انه في عندنا cycle يعني انتم عم تروحوا من some initial state وعم ترجعوا لنفس الانيشال state. So you're going from this initial state and then you are back through some given cycle to the same initial state. وما انه الدلتا بما انه الentropy is defined as a state variable يعني it only depends on the properties of a given equilibrium state, then we conclude that delta S is equal to 0 for a cyclic process, for a reversible cycle. لأنه بتكونوا عم تنطلقوا من ال S initial وعم ترجعوا على ال S initial. فبالتالي it's S initial minus S initial which is equal to 0. So this is why we say that delta S is integral of dq over t when you go from initial state to a final state in a cyclic process. هيدي السيركل بتاعني cycle. يعني عم تروحوا من الانيشال عم ترجعوا على الفاينل which is the same as the initial state. Delta S is equal to 0 in this case. So this you have to know. And finally, what about the entropy change in irreversible processes? So نحن مثل ما شفنا by the definition, the calculation of the change in entropy for a given system, it requires information about a reversible process which connects the initial to the final state. If you want to calculate the entropy change in a given irreversible process between two equilibrium states, we can do so actually, but we have to devise the reversible process, or well, actually we have to devise the the path from the initial state to the final state into a reversible process or a series of irreversible processes between the same two states. بتقول أنا بدي أروح من هيدا initial state على هيدا final state. So I can go from this initial to this final through يا إما one reversible process يا إما a combination of different reversible processes. And for each piece, you would calculate delta S by using delta S equals to integral of dq over t. وبعدين عم بتجاوبوا شو هي الدلتا اس ما بين الانيشال ستيت وما بين الفاينل ستيت، بيطلع معكم نفس النتيجه، لانه اجين مثل ما قلنا الانتروبي تشينج لها بس علاقه بالانيشال ستيت وبالفاينل ستيت. It does not depend on the path taken between the two. So a few comments, general comments, is that in general the total entropy and therefore the disorder always increase in irreversible process. بالirreversible process عموما so for example a gas can expand naturally, right? And if it expands naturally, it means its volume increases. And if the volume increases, that means that you have more volume where the molecules are moving, so you have more randomness of the position, and then you have more disorder. So the entropy always increases in the irreversible processes. And the second law states that the total entropy of an isolated system that undergoes a change cannot decrease. ممكن تكون عم بتقل الانتروبي على طول، يا اما تكون عم تكبر او it remains constant. إذا كان البروسيس irreversible, then the total entropy of an isolated system always increases. If we have a reversible process, then the total entropy of an isolated system remains constant. So بأحسن الأحوال الانتروبي بتضلها مثل ما هي، وإنما إذا ما كانت عم تكون مثل ما هي حكما بتكون عم تكبر ما بتكون عم تصغر. So this is it about the entropy. Now, just one last slide about the enthalpy, which I want to mention. So we have discussed the internal energy, different state variables. We have said that earlier. A given thermodynamic system in a given thermodynamic state is defined by different variables, among which we have the internal energy, we have the pressure, and we have the volume. And those were shown to be properties of a given thermodynamic system. Now, the combination of these three functions, it defines a new variable, which is called the enthalpy, which is defined as H is equal to U plus P times V. And the enthalpy is widely used in chemistry. We're not going to use it extensively in physics, but still it's worth to mention the definition of the enthalpy. So this is it for this chapter.